In this lesson, we will simplify radical expressions involving addition and subtraction. Like radicals, radicals that have the same index and the same radicand are called like radicals. So recall that index is the little number on the outer that tells what root, and the only one that doesn't have a number is square root, which we know the index is 2. The radicand is the number under the radical symbol. So again, if they have the same index, meaning the same root, and they have the same radicand, then those terms are called like terms or like radicals. On the other hand, if that is not the case, where they are not the same, then they are not like radicals. So the first example is an example of like radicals. Let's take a look at the second example. So first, let's check the indexes to see if they are the same root. And if you'll notice that the first one is square root, the second one in the second example is a cube root. So that means that the indexes are not the same, even though they have the same radicand. The fact that they don't have the same indexes, they cannot be like radicals. So in this case, this is what we call unlike radicals. Now, in order for you to be able to add or subtract radicals, they must be like radicals. You cannot add or subtract unlike radicals. Let's do some examples on adding and subtracting like radicals. So in the first example, A there, notice that they have the same index, meaning both are square root, and they also have the same radicand of 11. So therefore, these are like radicals. We can go ahead and proceed with adding them, and the way you add them is simply add the outside and keep the same radicand. So when I add 4 plus 8, that's going to leave me with 12 radical 11, because you keep your radicand there. Let's go to the second example. These are also like radicals. Notice the index are the same. They both are cube root, so we can add or subtract them. And also notice the radicands are the same. The radicand is 3x. So again, all we have to do is combine the outer terms and keep their index and radicand. So when I combine a 5 with a -7, that's going to give me -2 cube root of 3x. And there you have it. Let's do some more practice. Let's look at example C. So notice with example C, the radicands are not the same. So all we can do at this point is just simplify the radicals. So they're not perfect squares, square root of 20 and square root of 45, but they do have perfect inside them. So let's go ahead and extract the perfect out. We know that 20 has a perfect square of 4 inside, and 45 has a perfect square of 9 inside it. So you're going to solve the perfect, and it's going to go outside, remember, in front of the radical. If there's a number that's already outside, when you bring your answer outside, it will multiply with that number. So for the first term, square root of 4 is 2. We bring the 2 out, and that's going to leave me with 2 radical 5. For the second term, square root of 9 is 3. We bring the 3 out. It's going to multiply with 2 to give us 6. So then you'll have 6 radical 5. Now notice here that when you do that, the radicands of what's left over is the same. So they are like terms. So at that point, the fact that what you're left with here are like terms, you can go ahead and simply combine the numbers that are on the outside. So you have a 2 and a 6 outside. So you can go ahead and combine those two to give you a final answer of 8 radical 5. Let's look at example D. Example D, they are cube roots, and the first two are perfect cube roots. Well, I'm sorry, the first one is not a perfect cube root, but we can make it perfect because it has a perfect 27 in there. 27 times 2 is 54. For the 16, it is a perfect cube root, and then 2 is not a perfect cube root, so it's going to have to remain underneath the symbol. So let's go ahead and extract those perfects out. The cube root of 27 is 3, so the 3 is going to come outside, out front. The cube root of 8 is 2. The 2 is going to come outside and multiply with -5. So let's go ahead and do that. And at this point, if you take a look at the indexes, notice that they're all a 2. So that means that we can go ahead and combine them at this point because the indexes are all the same as cube root. They now have the same radicand there of 2. So all we need to do is just combine all those numbers outside and keep our radicand of 2. So let's see, we're going to have here 3, -10, and 1. Keep in mind, if you don't see a number out front, it is understood that there is a 1. So you must make sure you include that 1, very important. So let's move from left to right, combining these. Combining a 3 with a -7 is going to give, combining a 3 with a -10 will give me a -7. -7 combined with a 1 will give me a -6. So your answer would be -6 cube root of 2. And there you have it. Let's do another example here. So first of all, they do have the same index. They're all square root, but they do not have the same radicand. So at this point, we cannot add or subtract them. All we can do at this point is to go ahead and simplify them. So let's go ahead and simplify, taking the perfect squares out of the non-perfect. So the first and the last term, we need to take the perfect out. So recall, when we take the perfect and solve it, it comes outside in front. If there's a number out there, we will multiply our answer with that number. So we have here square root of 9 is 3. 3 is going to come out here in front. Same thing for the second term. Square root of 9 is 3. 3 will come out and multiply with -2 to give you -6 there. Square root of 36 is 6. 6 will come out front. So when we do so, what we're going to be combining here, and actually we cannot actually combine these out front, because let's take a look at our radicand. For the first term, we have a radicand of 3x. Second term, we have a radicand of x. Last term, we have a radicand of 2x. They are all different. You cannot combine any of them because they are not like terms. They don't meet that criteria. Remember, to be like radicals, you have to have the same index and the same radicand. Now they do have the same index, but they do not have the same radicand, so they are unlike radicals, which means at this point, all you can do is just simply leave it as is. But of course, with this middle term, let's go ahead and write -6 there. But that's it. You can't do any more to it. because they are unlike terms. And there you have it. Okay, last one. This one is a little bit challenging, but we can do it. Here you have fractions containing radicals, and I know fractions can be intimidating, especially unlike fractions, but you've done this before with regular fractions and rational expressions, so it's going to be similar to what you've done in Chapter 7 with solving unlike rational expressions. So first of all, the first thing I'm going to do here is to go ahead and simplify this radical square root of 45. There's a perfect 9 that we need to take out because 9 times 5 is 45. So now that we've simplified that, let's treat these like fractions. Unlike fractions, they have different denominators. You know that you cannot add or subtract fractions if the denominators are not the same. So what you have to do is find the LCD and then multiply each term with whatever it needs in order to be the LCD. So in this case you have 4 and 3, so your LCD is 12. What we need to do is in order to get 12 for the first term as a denominator, you'd have to multiply the top and bottom by 3. In order to get 12 in the denominator of the second term, you'd have to multiply the top and the bottom by 4. So let's go ahead and do that. So once you multiply the top and bottom by those, this is what you're left with. 9 radical 5 minus 4 radical 5 over 12. Now notice that the denominators are the same. And since the denominators are the same, we keep our denominator of 12 and the top, they're like radicals. All we have to do is combine the outside and keep radical 5. 9 take away 4 is going to give you 5. So what you're going to be left with is 5 radical 5 over 12. And there you have it. See? It wasn't that bad. Good job.